Wait for a little bit. Okay. Restart. So chapter 7 is about the kinetic energy and work. Okay, so there are two different type of mechanic energy in nature. So kinetic energy is one of them. And we are going to see the relation between energy and work. Okay. So first we are going to take a look at the concept. What is kinetic energy? So energy, see here, we have a different. So we are going to start with motion first. Energy is required for any sort of motion. And here, energy, usually we have unit that is in joules, okay, J. And it's a scalar quantity assigned to an object or a system of objects, and it can be changed from one form to another, and is conserved in a closed system. So total energy will be the same for a closed system. So there are different type of energy in nature. So you may have heard of nuclear energy, you may heard of heat energy, and you may heard of internal energy. So different type of energy. But in our class today, we are going to talk about kinetic energy. So kinetic, from the name, kinetic means motion. That means when an object is in motion, has speed v, it has kinetic energy. And also, there is different way to transfer energy from one form to another, like transfer from one like if you there are like chemical energy transferred into heat energy. And we also have like a battery is transferred from chemical energy to electric energy. So there are different ways to transfer energy, and work is just one of them. So here we are going to see kinetic energy. Okay, when an object is in motion, it has kinetic energy, and also the faster an object moves, you can take a look at here. Faster the object moves, the greater its kinetic energy. So bigger speed, bigger kinetic energy. And also kinetic energy is 0 for a stationary object. So kinetic means object in motion. If the object is not in motion, then it does not have kinetic energy. And also, we have the formula to calculate the kinetic energy. So see here, if we have, we use, so kinetic energy, usually we use letter K to represent it. And if the mass of the object is m, so the calculation is 1/2 mv squared. Okay, 1/2 mv squared. And the unit for kinetic energy is joule. And the joule is the same as, because m is the mass, V is the speed, so it's kilogram times meters per second squared. So this is the unit. But usually we just use joule, and a kilogram, meter, second as a base unit. So it can be expressed as the base unit. So we know move object in motion have kinetic energy. Kinetic energy depends on the mass, also depend on the speed. So this is kinetic energy. And we have a calculation here. So energy released by two colliding trains with given weight and acceleration from rest. And this problem we need some information given to you. So here we have the weight. So here, so colliding train. Okay, the weight of the train is 1.22 times 10 to the power of 5th kilogram. Okay, and also the speed. Okay. Here we have, oh, actually so from rest, we are going to have the acceleration of the train will be equal to 0.26 meters per second square. and the train brought to stop in 3.2 times 10 to the power of 3 meters. Hey, why my pen is so... Okay, so with given, so the acceleration of the train is 0.02 and the train brought to a stop in this distance. So you are going to calculate the energy released, okay? So here, if you want to calculate energy, we know kinetic energy will be equal to 1/2 mv squared. So if you want to calculate kinetic energy, you want to find the speed first. So they are brought to a stop. So the acceleration try to make the object wait for a little bit. So acceleration is 0.26 meter. Actually, we shouldn't say brought to a stop. It's the train travels for. If you say the train travels. So it's starting from rest. So the train travels for 3.2 times 10 to the power of 3 meters. Okay, okay. So acceleration, so basically it's we have two train, okay, and both of them are accelerating, and this train, okay, they collide here, and the moving, okay, so they are both moving this way and this way. So the moving distance is 3.2 times 10 to the power of 3 meters. And then they collide, okay? So you want to calculate the kinetic energy here because this V initial is 0 meters per second. You want to calculate the V final here. Yeah, okay, so that is right. So here you want to calculate V final. We can use the kinetic equation to calculate that because you know your initial is 0, you know your acceleration is 0.26, and you know the distance traveled by the train is 3.2 times 10 to the power of 3 meters. So you can calculate the final speed, which is 40.6 meters per second, because your initial is starting from rest is 0, acceleration is 0.26, and the travel distance is 3.2 times 10 to the power of 3 meter. And then you will calculate the speed when they collide, which is 40.8 meters per second. And the weight of the chain is given to you 1.22 times 10 to the power 5 kilograms. So you can get this. And then because you have two train, why we have two here? It's the two train they collide into each other. Okay. So that's why each one of them has kinetic energy, which is 1/2 m. So this is a V final square, 1/2 V square, 1/2 mv square, and you have two of them. So this is the total kinetic energy. So using the kinetic equation, you will be able to get your speed. And after that, you can use the kinetic energy equation to calculate the kinetic energy. Okay, so this is the problem. And then we are going to calculate work. So what is work? So work is the measurement. I'm going to put it here. What is work? So work is the measurement of how much a force is accomplished Okay, so when there is a force on the object, so here down on the object by the force, and if you have, let's say if you have an object, you are moving the object using the force F. So the work done by this force is the measurement of how much the force is accomplished. So you may move this object from here to here, and the motion is how much the object is accomplished, how much the force is accomplished. So here we can take a look at the detailed explanation. So account for changes in kinetic energy by saying energy has been transferred to or from the object. So if the kinetic energy changed, then the energy must be transferred in or transferred out from another form. So in a transfer of energy by a force, so if you want to use force to transfer energy, and then we need to know what is the work. So work is how much is accomplished by a force. And the work, W, is energy transferred to or from an object by means of a force acting on the object. Energy transfer to the object is positive work, and energy transfer from the object is negative work. So the force can either do positive or negative work on the object. So let's see how to calculate the work. So here, one thing you need to know about work is to do work on an object, energy must be transferred. So there may be you have a force acting on the object, but the object moves this way, and this force actually did nothing because you want to move the object from position 1 to position 2, but this force is moving the object upward. It has nothing to do along this direction. So this force actually didn't do any work. You must have a force like this to do work. So not necessarily a force applied on an object will do work. Okay, so make sure you understand this concept. And here we have, let's finish the work first, and then we go back to here. Okay, so to calculate the work a force does on an object, the object moves through some displacement. So say here it's, if we move the object from here to here, it must move it. Okay, so if the object didn't move, then we say the force didn't do anything. So the displacement from here to here is d. So you can do this. And how to calculate work? It's work equals to force dot displacement. And if you know the angle phi here is actually equal to F times D times cosine phi. Okay, so be very careful. So this is how to calculate the work. And the work also have unit that is joule. So force, this F here is the magnitude of the force. D here is the displacement of the object, and the cosine phi, phi is the angle. And here, why work can be negative? Think about if you have a force. Hmm? Hmm? Wait, sorry. Think about, so here we have move to 1, from 1 to 2. Think about if you have a force that is moving this way, this is your phi. And this phi here, if it's bigger than 90 degrees, then cosine phi will be a negative value, right? So if you have the displacement in this direction, but the force applied on the object, it's at an angle bigger than 90 degrees to the direction of motion, then the force may do negative work. So in vector form, we write it as W equals to Fd, okay? And here on this equation, force is constant and object is rigid. Rigid means the shape will not change. And the work can all can be positive or negative. So it could be negative if your cosine phi is bigger than 90. And also some specific angle because your work equals to F times D times cosine phi. So if your phi equals to 0, cosine phi is 1. That means object move from here to here, it's in the same direction, so the force is this, so angle is 0. And you may also have phi equals to 90 degree, which the force looks like this. But then your cosine phi will be equal to 0 because cosine 90 is 0. And in this case, your work equals to 0, okay? When the angle is at a 90 degree to the direction of motion, the work done by the force is 0. And also you have phi equals to 180, and then your cosine phi will be equal to -1. And then that means the force is doing negative work. So it all depends on how the force is being applied to the object. Okay. And see here, what is your phi? Phi is here. So actually, it's the component that is parallel to the direction of motion that is doing the work, okay? So this component will not do work only in this component. So it's the component parallel to the motion, parallel to the direction of motion that is doing the work. And also work has a standard unit. SI unit is joule, but in British system, we also have foot-pound, but we use joule, okay? We don't use other units. Okay. And then we take a look at this. If we know the object is doing work to the system, what will change? Okay. So a force does positive work when it has a vector component in the same direction as the displacement, and it does negative work when it has a vector component in the opposite direction. So that means when our angle is bigger than 90, then you are going to have a vector component in the opposite direction. And it does 0 work when it has no such vector component. That means the force is perpendicular to the direction of motion, okay? So for two or more forces, the net work is the sum of the work done by all individual forces. So it's done by all of the forces, okay? So you need to add work 1, if you have force 1, force 2, force 3. If you want to calculate the net work, you need to find all the forces and the work done by all the forces and calculate them. But there is another way to do the calculation. We will talk about that later. It's work and energy theorem. So we have two methods to calculate net work. We can find all the works and sum the individual work terms, and we can also get the net force and calculate the work done by the net force. And then we also have calculate the change of kinetic energy. So we can take a look at next slide. Okay, so we will have work and energy theorem. What does this tells you is what work will do to our system. So here, going to write here, work and energy theorem. It's if work is applied to a system, then the K means kinetic energy will change. Okay, so the change of kinetic energy, which is delta K. Okay, the change of kinetic energy, delta K will be equal to the work applied. So I'm going to write if work W work W is applied to the system, then the kinetic energy K will change. And how to calculate the change is delta K will be equal to W. So you can say delta K equals to the work. What is delta K? Delta K is the change in kinetic energy. So it's final kinetic energy minus initial kinetic energy. And we can write it like this. It's K final equals to K initial plus W. So why this equation is right? Think about you have an object, right? So you have initial kinetic energy K initial. So if you have work, you are doing something to the object. So this is input work. Okay, so after the input work W, what happened in the end? So this is final. After you finish, put all the work in, your K final will be equal to, so this goes to here, is K final will be equal to K initial plus the work in, right? Because these two, this is the initial, this is the input. Input plus initial will be the output, right? So that's the final. And this equation also shows you conservation of energy. It's the input plus the initial will be equal to the output, okay? So the work and energy theorem holds for positive and also negative work. So if the energy is, so if kinetic energy is 5 joules initially, we transfer 2 joules to the particle, then we have 5 plus 2, which is 7 joules. But if we have transferred 2 joules out of the particle, so from the particle, so you should do 5 minus 2, you are going to get 3 joules, okay? So work can be negative. So if you have input that is negative, it didn't increase the kinetic energy, it will decrease the kinetic energy, okay? So we can take a look at some. These are the some. This example involves some of the calculation. So you can take a look at that. A particle. A particle moves along an x-axis. So does the kinetic energy of the particle increase, decrease, or remain the same if the particle's velocity changes from -3 to -2, -2 to 2, and in each situation, is the work done on the particle positive, negative, or 0? So how to calculate this? It's, see, for A, our initial kinetic energy will be equal to 1/2 mv squared. So it's 1/2 3 times 1/2 m times 3 squared, right? So you will get 4.5 m. And then B, oh, not B, your final kinetic energy. Your final kinetic energy, you should do 1/2 mv final square, and you are going to get 1/2 m2 square. So you are going to get 2m, right? Mass cannot be negative. So you can see it's the initial kinetic energy is bigger than the final because 4.5 m to 2m. So the energy decreases, right? So this is bigger than this, so it decreases. You can see here, energy decreases. And from -2 to 2, so if this is -2 square, so for B, your K initial -2 square is still 1/2 m. So you are also going to get 2m, right? And then 2m, you do final is also 2m, so the energy remains the same. So this is going from 2m to 2m, okay? And also here, in each situation, what is the work done? So this one here, you have decreased kinetic energy. Decreased kinetic energy, that means work is negative. And if you have 0 change, delta K is 0, then you do not have work. But if you do have positive kinetic energy, change, then your work is positive. Okay, energy decrease, negative work. Energy increase, positive work. And then we are going to see the work done by different forces. So the first one we are going to talk about is work done by gravitational force. And then we are going to see a potential energy. So work done by, so calculate the work as we could for any force. The work done by gravitational force is the same way as we calculate the work done by anything. So if you have an object moving up, and moved from here to here, initial position to final position from 1 to 2 is D. And then this is our gravitational force Fg. So our W will be equal to mg, which is Fg, times D times cosine phi. What is the phi here? The phi is this big angle, right? Big angle, this phi should be equal to 180. So that's why you are going to see mgd cosine 180, and then you are going to get a negative mg. So this is for going up object. So this is when, okay, you see the negative sign, that means your displacement goes up. Okay, but when we also have another situation, it's when we have a falling object. So this is your initial and it goes to here. This is your final. So this is your displacement D going down, and your gravitational force is mg here. Your phi is 0 degree because it goes down. So that's why we have cosine 0 and it's positive mgd. So in the two situations, we have the same gravitational force, but it's actually doing different work. Okay, so be very careful of that. So work done in lifting or rolling an object, applying an upward force. So here, what we have is here, the change of kinetic energy will be equal to the work done on the object, right? So this is work and kinetic energy theorem, which is from here, okay? So change of kinetic energy is final kinetic energy minus the initial kinetic energy. But for the work, we have applied force, applying upward force. So WA here means work done by applied force. And also, we have another force, it's our gravitational force. So this is the work done by gravitational force. So change of kinetic energy will be equal to the work done by the two forces. The work here should be the sum of all the works. So we add these two terms together. And for a stationary object, the kinetic energies are 0. So our work done by applied force will be equal to negative work done by the gravitational force. So usually we say we need to overcome the work done by gravitational force to lift up an object. Okay, so be very careful with how we do the calculation. So in other words, for an applied lifting force, WA will be equal to negative the mgd cosine phi because it equals to negative WG, okay? So this is that. And applies regardless of the path. So it only depends on how much the gravitational force is, how much work the gravitational force is done on the object. So we don't need to worry about this. This is just the gravitational force. If it's moving up, the gravitational force is doing negative work, so our applied force is doing positive work. And if the object is moving down, our gravitational force is doing positive work, but our applied force is doing negative work. Okay, so this is how to calculate the work done by gravitational force. And we have an example here. Yeah, let's go with the concept. It's very easy, the concept. So here, you are a passenger here and being pulled up by a ski rope. So have a ski rope here. So the tension, so let's take a look at all the forces applied on the slide here. We have gravitational force, right, Fg. We also have the tension here, and we also have the normal force here. Okay, so we have these three forces acting on the object, and assume this ramp is frictionless, so we don't have frictional force. Okay, so say think about how to calculate. Okay, let me ask you the work. So the work done by the normal force, the work done by the tension, and the work done by the gravitational force. Which one of them are positive, and which one of them are negative, and which one of them are zero? So think about tension. Tension and this D have the same direction. So when you do cosine phi, phi is zero. Zero is positive. Cosine phi equals to 1. Cosine 0 equals to 1. So this is positive. And this is negative, right? Because you have to calculate direction of motion. You are calculating this big angle here is your phi. Okay. And this phi here actually equals to 90 plus theta. So that's why your phi is bigger than 90 degrees. So cosine phi is negative. So this is negative, but for normal force, this is 90. So phi equals to 90. And this is phi equals to 0. So 90 then it's 0. So be very careful. It's tension does positive work, gravitational force does negative work, and normal force does not do any work. Okay. And also, we have in an elevator. Okay. So in the elevator is also, if you are going to be very careful, it's being lowered down. Okay, lower down. This is your displacement. So say here, you have tension and you have gravitational force, right? So the gravitational force and the displacement is in the same direction. So phi equals to 0, and then cosine phi will be equal to 1. So the work is positive for gravitational force. But here your phi is 180, and then cosine 180 equals to -1, so the work is negative. So you can see here how the work is being done on the objects. Okay? And we also have work done by a spring force. We have to understand what is spring force first, and then we can calculate the work. Okay, so let's take a look at the spring force. What is spring force? You know how spring look like? It's usually like this. This is like a typical spring. The reason we study spring force is because in microscopic world, if you see the atoms are, so there are a lot of atoms are connected. Okay. And the force between the atoms looks like spring force, okay? So if you have a very simplified model, you can see all the atoms, they are actually connected by springs, and you can calculate those forces. So that's why we are going to study spring force. Spring force, we have general picture look like this. So there are different things relates to the spring, it's okay, F. Okay, so the spring force depends on the stretchment or compression. So we are going to have delta X. So delta X is either the stretchment or compression of the spring. So the bigger the stretchment and the bigger the compression, the bigger the force you need to apply on the spring to make it happen. And we also have a spring constant, it's K here. So F equals to Kx. K is what we call spring constant. It's measuring the stiffness of the spring. So if the spring is very stiff, then you have a big K. And if your spring have small k, then that means it's a very loose spring. Okay, so if you understand this, we can go over the concept. A spring force is the variable force from a spring, and a spring force has a particular mathematical form, looks like this. It depends on the stretchment or compression, and also we have a proportionality K here, is what we call spring constant. And many forces in nature have this form, like the forces between the atoms, okay? So we have this figure A shows the spring is in its relaxed state. So we do not have compression or stretchment. So it is neither compressed nor extended. So no force is applied. And if we stretch or extend the spring, it resists and exerts a restoring force that attempt to return to the relaxed state. And how to calculate that is Fs will be equal to, this is the force by the spring, okay? By spring. So if it is stretched, there is a force by the spring, try to make it going back. So force by spring will be equal to negative Kd, and D here is the compression or stretchment, okay? So the negative sign represents that the force always opposes the displacement. So if you have stretchment, it tries to come back, and if you have compression, it tries to resist. So here, that's why we have this negative sign. The force by the spring always try to oppose the displacement. And the spring constant K, you have this K here, is a measurement of the stiffness of the spring. So this is a variable force. So F is a function of the D, and it shows a linear relation between F and D. So if we have the stretchment or compression along X direction, then we can write it like this. It's Fx equals to negative Kx. Okay, so remember this equation. This is the spring equation, and it's very important. Okay, Fx equals to negative Kx. And then we can find the work done by the spring. You can do an integration, because what is that? W will be equal to F D. And here this is Fx. But our F is different. So that's why we will have changing W will be equal to F delta X. So basically it's the same as dW will be equal to F dx. And then you do an integration. Because F is changing with X, you cannot have a constant here. You have to write it as F delta X. So this is the integration we need to have. And you have a negative sign because this is negative. So work done by the spring, when you put kx in the equation, you are going to get 1/2 kx initial square minus 1/2 kx final square. Because you put a kx in here, you are going to get 1/2 kx square, and then x initial x final negative, and then put it in, you are going to get this. Okay. So do the integration, you are going to get the work done by the spring will be equal to 1/2 kx initial square minus 1/2 kx final square. So depend on the stretchment, initial stretchment and the final stretchment, or initial compression and final compression. So the work can be positive or negative, depend on the net energy transfer. Okay, depend on how the initial and the position, final position looks like. So take a look at this. Work is positive if the block end up closer to the relaxed position because it's K initial and K final. So if it's closer, then K initial is bigger than K final, and then you can get WS is positive. But it's negative if it ends further away, and it's zero if it ends up the same distance from x equals to 0. So for an initial position x equals to 0, the work done by the spring will be equal to negative 1/2 kx squared. Okay. So so this is the work done by the spring. And for an applied force where the initial and the final kinetic energy are 0, so WA will be equal to negative WS. So one is work done by the spring, the other one is force applied on the spring. So these two will be equal to 0 because if you have change of kinetic energy equals to 0, it equals to work by the applied force plus the work by the spring. So applied force will be equal to negative spring. This equals 0. So this is that. So if a block that is attached to a spring is stationary before and after displacement, then the work done on it by the applied force displacing it is the negative of the work done on it by the spring force. So basically this is applied force equals to the work done by the applied force equals to the negative work done by the spring. So this is that. Now we can take a look at the checkpoint. So for the three situations, the initial and the final positions respectively are -3, 2, 2, 3, -2, and 2. In each situation, is the work done by the spring on the block positive, negative, or 0? So if initial is negative, final is 2. Final, see here, we should do 1/2 kx initial square minus 1/2 kx final square. This is WS. Okay, so if you put a -3 here, 2 here, -3 you get 9, 2 you get 4. 9 is bigger than 4, so A is positive. Okay, but for B is 2, so this is B. 2 and 3. 2 minus 2 square, you are going to get a 4. And 3 square, you are going to get 9. So you are going to get -5. And then -5. So actually 1/2 4k minus 1/2 9k, you are going to get a negative value. But if you have going from 2 to 2, then it's 4 minus 4, so it's 0. Okay. So it's only depend on the initial position and the final position. So this is that. And we also have this section, we don't need to understand it. It's work done by a general variable force. And this section is being skipped from our class because we will do if you are going to take mechanics, it's a higher level physics class, you are going to learn this a little bit more because it involves a lot of integration in here, which is not required in our class. Okay, so that's variable force. So section 7.5 is skipped. Okay, work done by a general variable force, but we are going to go to power. Okay, 7.6. So first, we are going to take a look at definition of power. So power is the measurement of how fast is the work done on the object. So it's the time rate at which a force does work. So work divided by time actually is our power. So a force does work in this amount of time, then the power will be equal to W divided by delta T. And we also have instantaneous power is we shrink delta T to an instant, okay, to 0. So you are going to have power equals to dW over dt, and then the unit. So here, this is joules per second. So unit for power is watts, okay, watt. It's joules per second. So work and energy theorem can also be written as power multiplied by time, okay? So your work is power multiplied by time, okay? And there are different units for work. We have kilowatt hour. So this is kilowatt hour. So kilowatt is 1,000 watt, and an hour is 3,600 seconds. So you can calculate this in joules. It's 33.6 times 10 to the power 6 joules. Okay, so kilowatt hour. And kilowatt hour is usually you have to measure like the electricity consumed in your household, and we use this value because joule is a relatively small measurement of power, and yeah, you are going to get a very big value if you use it for the consumption of electricity. Okay. And here we have different versions for power. You have P will be equal to dW over dt. And then if we have a constant force, so it's F cosine phi dx. So dx over dt. Dx over dt, you are going to get a velocity. So power is Fv cosine phi. And you can also write it as P equals to vector F dot vector V. Okay, V is the what is V? V is the velocity, okay? So the velocity of the force, so how fast the force moves. Okay. So we can take a look at the checkpoint here. Is a block moves with uniform circular motion because a cord tied to the block is anchored at the center of a circle. So what is the power due to the force on the block from the cord? Positive, negative, or 0? Okay. This is a very interesting problem. We have the tension here, and the tension is the force by the cord, and we have the velocity here. Like this is doing circular motion, right? And then why is 0? Think about this angle here. The velocity and your tension. Tension is towards the center, but your velocity is along the tangent line of the path. So this is always 90 degree. And what is cosine 90? Cosine 90 is 0. So the power is 0. The work done by this force is also 0. Okay, now we finished this chapter 6. So I do want to, this is a summary, we don't have to go over that, but I do want to remind you is that we will have 2 labs tomorrow, okay? So make sure you come to lab tomorrow at 11 a.m. I'll send you guys an email about it, okay? And try to do your homework. I checked your homework for chapter 5. I think only 7 of you did the chapter 5, and only 2 of you did chapter 6. Yeah, only 3 of you did chapter 6. Do your homework on time, okay? So you can keep up with the things we are talking about in the lecture. Okay, so I think that will be all, and I'll see you guys in person tomorrow. Okay, bye bye. Bye bye.